There is an assumption so deeply embedded in our thinking that most of us never notice we are making it. We assume that tomorrow will be like today, that the sky will still be blue, that the oceans will still be liquid, that the air will still be breathable, that the forests and the grasslands and the reefs and the tundra will still be there, still occupied by the extraordinary, improbable abundance of life that we have inherited from 4 billion years of evolution. We do not think about this assumption because it has been true for every single day of our lives, and for every day of every human life before ours, and for every day of every creature that has ever lived on this planet. The conditions have changed. Ice ages have come and gone. Continents have drifted. Species have risen and fallen. But the fundamental habitability of Earth has never wavered. Not once in 4 billion years has this planet become completely uninhabitable. That record will not hold forever. The sun is aging. It has been aging since the day it ignited 4.6 billion years ago. And as it ages, it brightens. Every 100 million years, the sun's luminosity increases by approximately 1%. This seems small. At this moment, it is too small to measure without sophisticated instruments, but sustained over hundreds of millions of years, over billions of years. 1% every 100 million years becomes a transformation. The Earth of 500 million years from now will receive more solar energy than it does today. The Earth of 1 billion years from now will be dramatically hotter than it is today. The Earth of 1.5 billion years from now will have no liquid oceans. And the Earth of 5 to 6 billion years from now will likely be engulfed by the expanding envelope of a red giant star, the star we currently call our Sun. These are not catastrophic predictions. They are not worst-case scenarios or models built on uncertain assumptions. They are the outputs of stellar physics, one of the most precisely understood areas of science, applied to a star we have been observing for centuries and modeling with equations for decades. The timeline has uncertainties in the tens of millions of years in some places, but the broad shape of what is coming is not in doubt. This documentary travels through that timeline, not with despair, not with alarm, but with the same quiet wonder that should accompany any honest contemplation of deep time, because the story of how life ends on Earth is, in its own way, as extraordinary as the story of how it began. Let us go, not forward into an imagined future, forward into a calculated one. Before we begin the journey, we need to equip ourselves with the right tools for thinking, because the timescales involved in this documentary, hundreds of millions of years, billions of years, are genuinely outside the range of human intuition. We did not evolve to think about billions of years. Our brains are adapted to think about lifetimes, generations at most. The idea of 1 million years feels abstract, let alone 1 billion. So let us build a scale. Let us compress the entire history of Earth, 4.6 billion years, into a single calendar year. 1 year. January 1st is the formation of the Earth. December 31st, 11:59 at night, is right now. On this scale, the first life on Earth, simple microbial cells, appears in February. Not February the 1st. February is the entire early Archean eon. Complex cells, eukaryotes, cells with a nucleus, do not appear until July. The first multicellular organisms appear in late October. The Cambrian explosion, the sudden diversification of complex animal life, happens on November 14th. The first land plants arrive on November 22nd. The first forests on November 24th. Dinosaurs appear on December 11th. They rule the Earth until December 26th, when an asteroid ends their reign and the age of mammals begins. The entire existence of Dinosaurs, 170 million. Years of dominance. Fits between December 11th and December 26th. Anatomically modern humans appear at 11:58 and 42 seconds on December 31st. All of recorded history, every civilization, every empire, every war, and every discovery fits into the last 5 seconds before midnight. Now consider what we are about to discuss. Pangea Ultima forms in 250 million years. On our calendar, that is about 20 days from now. The last plant dies in 500 million years, about 40 days from now. The oxygen in the atmosphere collapses in 1 billion years, about 79 days into next year. The oceans evaporate in 1.5 billion years, 119 days into next year. These events feel distant because the numbers are large, but on the scale of the universe, they are close. They are the next chapter in a story that is already 4.6 billion years old. And understanding how they will unfold requires understanding the forces that are already shaping them. The slow brightening of the sun, the relentless movement of tectonic plates, and the cascading effects of these changes on the chemistry of the atmosphere and oceans. The study of deep time, geologic time, the vast expanse of Earth's past and future, has a specific emotional quality that is unlike any other scientific contemplation. It is not the scale of space, which produces awe at distances. It is the scale of time which produces something quieter, something like humility, something like the feeling of standing at the edge of the ocean and understanding, in a visceral rather than intellectual way, that you are very small and the ocean is very large. The geologist John McPhee, who coined the phrase deep time in his 1981 book Basin and Range, described what happens when a person truly internalizes geological time. He wrote that the mind, faced with the abyss of time, undergoes a kind of alteration. The familiar categories of past and present begin to blur. The events of human history recede to a vanishing point. What remains is something difficult to describe. A sense of being embedded in a process so vast and so old that the word history no longer quite applies. We are about to travel through that abyss, into a future that no human will ever see, a future that is nevertheless as real as the past, as certain in its broad outlines as anything in science can be. The future of the Earth is written in the physics of the sun and the chemistry of the atmosphere, and it has already been calculated. We begin our journey 250 million years into the future, a moment that, on our compressed calendar, is only 20 days away. The Earth of 250 million years from now will be recognizable as Earth. It will have an atmosphere. It will have liquid oceans, though smaller and warmer than today's. It will have life, but it will be a profoundly different world from the one we know, shaped by the most fundamental geological process operating on our planet: plate tectonics. The continents are not fixed. They never have been. Over the last 250 million years, the supercontinent Pangea has broken apart. The Atlantic Ocean has opened. India has collided with Asia, raising the Himalayas. Africa has begun to collide with Europe. And the process continues. The plates that carry the continents are still moving, still drifting, still slowly rearranging the geography of Earth at rates of a few centimeters per year. In 250 million years, those movements will have accumulated to produce something new, a new supercontinent. Geologists call it Pangea Ultima, sometimes Pangea Proxima. It forms when the Americas drift eastward, the Atlantic Ocean closes, and the landmasses of Europe, Asia, Africa, and the Americas merge into a single enormous continent centered somewhere near the tropics. The formation of Pangea Ultima will be gradual, Not a single collision, but a series of mergers over tens of millions of years. But the end result, modeled in a 2023 study published in the journal Nature Geoscience by Alexander Farnsworth and colleagues at the University of Bristol and other institutions, is deeply problematic for the dominant land animals of our current era, mammals. The study ran sophisticated climate models for Pangaea ultima. Their findings were striking. Up to 92% of Earth's land area may become uninhabitable for most mammals within Pangaea ultima. The reasons are interconnected. First, continental interiors dry out. The ocean moderates climate. Coastal regions have milder temperatures, more rain, more stable conditions. Interior continental regions, far from the ocean's moderating influence, experience temperature extremes. Pangaea, when it existed 250 million years ago, had vast interior deserts. Pangaea ultima, being even larger, will have even more extreme interior conditions. Second, the sun will be about 2 to 3% brighter in 250 million years than it is today. This may seem small, but applied globally and sustained over geological time, it is sufficient to push global average temperatures significantly higher. The study found that global mean surface temperatures in Pangaea ultima may reach between 40 and 70 degrees Celsius, compared to today's average of approximately 15 degrees. At temperatures of 40 to 70 degrees, sustained indefinitely, most mammalian biology fails. Mammals, as warm-blooded endotherms, require the ability to regulate their body temperature. Above approximately 40 degrees Celsius, the biochemistry that maintains body temperature begins to fail. Third, the continental collision that creates Pangaea ultima will trigger increased volcanic activity along the collision zones. Volcanoes release carbon dioxide. In the current climate, the carbon silicate cycle removes this carbon dioxide through weathering and ocean absorption. But in a hotter world with a brighter sun, the carbon silicate cycle operates less efficiently. More volcanic carbon dioxide stays in the atmosphere, amplifying the warming. The paper by Farnsworth's team was blunt about the implications. Hannah Davies, one of the co-authors, said, quote, "It does seem like life is going to have a bit more of a hard time in the future. It is a bit depressing." End quote. The lead author, Alexander Farnsworth, speculated that if humans were still around in 250 million years, they might need to adapt to a world resembling the landscape of the 1965 science fiction novel Dune. Desert survivors, cave dwellers, creatures adapted to extreme heat and scarcity of water. But it is important not to confuse what will happen in 250 million years with what has already been determined. Many things may change on that timescale. Some researchers argue that the carbon silicate cycle, even under hotter conditions, may remain effective enough to limit the warming. The biosphere itself may evolve new adaptations. Life on Earth has survived conditions arguably as severe as anything Pangaea ultima will produce. The Permian-Triassic extinction event 252 million years ago killed 90% of all species and life recovered. Recovery takes time. Recovery requires survivors. But the history of life on Earth is a history of survival through catastrophe. Nevertheless, the formation of Pangaea ultima represents the first major waypoint in deep time, where the conditions for the life we know will be severely tested. Most of the mammalian species alive today, if they have survived this long, which is unlikely given their typical geological lifespans, will not survive the thermal and arid conditions of a Pangaea ultima world. The world of 250 million years from now will belong to something more heat tolerant, more water efficient, more adapted to the conditions that the brightening sun is already, slowly, creating. Approximately 500 million years from now, something will happen that has not happened on Earth for almost 4 billion years. The last photosynthesizing plant will die, not because of a catastrophe, not because of a disease or a predator or an asteroid, but because the concentration of carbon dioxide in Earth's atmosphere will drop below the minimum level required for photosynthesis. The plants will run out of the one ingredient they need to convert sunlight into energy. The mechanism is the carbon-silicate cycle, the same cycle we discussed when explaining plate tectonics. The carbon-silicate cycle works as follows. Carbon dioxide in the atmosphere dissolves in rainwater, forming weak carbonic acid. This acid weathers silicate rocks, combining with calcium and magnesium to form carbonate minerals. These carbonates are carried by rivers to the oceans, where they settle into the seafloor. The seafloor is subducted under continental plates at tectonic boundaries. Deep underground, heat releases the carbon dioxide from the carbonates, and it returns to the atmosphere through volcanism. This cycle keeps the carbon dioxide concentration in the atmosphere roughly balanced over geological time, but it has a temperature dependence. When the planet is warmer, as it will be due to the brightening sun, chemical weathering accelerates. Silicate rocks weather faster in a warmer, wetter climate. More carbon dioxide is drawn down from the atmosphere and locked into carbonate rocks. The drawdown exceeds the volcanic replenishment. The atmospheric carbon dioxide concentration falls. This is already happening in geological terms. The current carbon dioxide concentration in Earth's atmosphere, approximately 422 parts per million, is historically low. The Earth of 300 million years ago had carbon dioxide concentrations many times higher. Long-term geological trends, absent human intervention, were pointing toward a future of declining carbon dioxide. The brightening sun will accelerate this trend. In 500 million years, the calculation suggests the atmospheric carbon dioxide concentration will fall below 150 parts per million, the minimum level required for C3 photosynthesis, the form of photosynthesis used by most plants today. Below this level, C3 plants, which include most trees, most food crops, and most of what we think of as a plant, cannot fix carbon efficiently enough to survive. C4 plants, a more efficient photosynthetic pathway used by grasses, maize and sugarcane, can survive at lower carbon dioxide concentrations. They will outlast the C3 plants by approximately 300 million years. At approximately 800 million years from now, the atmospheric carbon dioxide will drop below the minimum level that C4 photosynthesis can sustain, and the last plant on Earth will die. The death of plant life will not be instantaneous. It will be a slow, uneven retreat. The plants that use the most efficient photosynthetic pathways, in the most favorable locations, high elevations, areas with the most sunlight, areas where the remaining carbon dioxide is least diluted, will be the last survivors. They will not know they are the last. They will not know anything. They will simply be alive until they are not, in a process as quiet and inevitable as the brightening of the sun that caused it. The death of plants will cascade. Plants are the foundation of most terrestrial ecosystems. They produce the oxygen that animals breathe. They fix carbon dioxide in forms that animals can eat. They stabilize soils and moderate water cycles. They are, in the most literal sense, what makes the land habitable for complex life. Without plants, the oxygen production that has kept Earth's atmosphere breathable for the last 550 million years will stop. What happens next is not immediate suffocation. The oxygen in the atmosphere is a large reservoir, and consuming it requires time. But without replenishment, it begins its slow decline, and by 1 billion years from now, the decline becomes a collapse. In 2021, a team of researchers at Toho University in Japan, led by Kazumi Ozaki and Christopher Reinhard, published a paper in Nature Geoscience with a title that has become one of the most cited phrases in discussions of Earth's long-term future: the future lifespan of Earth's oxygenated atmosphere. To write it, they built a detailed computer model of the coupled evolution of Earth's atmosphere, biosphere, and geosphere, the three systems that interact to determine what gases are present in the air we breathe. They ran the model 400,000 times, varying the uncertain parameters across their plausible ranges. They then calculated the probability distribution for when Earth's atmospheric oxygen would drop below the level required to sustain complex animal life. Their best estimate, 1.08 billion years from now, with an uncertainty range of roughly 0.9 to 1.4 billion years. 1 billion years. That sounds reassuring. An enormous amount of time. But the mechanism behind the collapse is worth understanding, because it is already in motion. As the sun brightens, the planet warms. The warmer planet accelerates the weathering of silicate rocks. More carbon dioxide is drawn down from the atmosphere. Photosynthesis weakens and eventually stops. Oxygen production, which depends entirely on photosynthesis, slows and stops. But oxygen is consumed continuously by geological and chemical processes. Iron in rocks oxidizes, consuming atmospheric oxygen. Organic carbon in sediments oxidizes when exposed at the surface. Volcanic gases include reduced compounds that react with oxygen. Without photosynthesis constantly replenishing the oxygen supply, these sinks will gradually drain the atmospheric reservoir. The transition will not be gradual and smooth. The model by Ozaki and Reinhard found that the collapse of atmospheric oxygen will be relatively rapid once it begins. Not a slow decline over hundreds of millions of years, but a transition from an oxygen-rich atmosphere to an oxygen-depleted one on a timescale of millions to tens of millions of years. Fast, geologically speaking. Sudden, if you are watching it happen. The end state, the atmosphere that replaces the oxygen-rich one we breathe today, will resemble something closer to what Earth's atmosphere looked like 3 billion years ago, before the great oxidation event, before photosynthesis transformed this planet's air. High methane concentrations, very low oxygen, sulfur compounds, an atmosphere that would kill a human within minutes of breathing it. Not because it is poisonous in the direct sense, but because it contains almost no oxygen for the biochemistry that powers our cells. The paper by Ozaki and Reinhard put this in stark terms. Once the oxygen collapses, Ozaki said, quote, "We slowly revert to a high methane, low oxygen hellscape that looks more like ancient Earth than anything remotely livable." End quote, a hellscape. Not the catastrophic kind, not fire and explosion and the violent end of things, but the slow, quiet, chemical kind. The atmosphere that made Earth unique in the solar system. The oxygen-rich air that is the signature of life on a planet-wide scale will be gone. Replaced by the kind of air that existed before life was complex enough to produce oxygen. What survives? The question is important, because the oxygen collapse is not the end of all life. It is the end of complex aerobic life, life that depends on oxygen for its metabolism. What survives in a low-oxygen, methane-rich atmosphere are the organisms that thrived before oxygen dominated the Earth. Anaerobic bacteria, archaea, single-celled organisms that do not need oxygen to live, and indeed for which oxygen is toxic. The microbial world that preceded complex life will, in a sense, reclaim the Earth. The age of animals, plants, and fungi the familiar visible world of complex multicellular life will be a long chapter, more than 600 million years, but a chapter, and after it ends, the planet will not be dead. It will be microbial again. 1 billion years from now, the oxygen is gone, the complex life is gone, the microbial world persists. 500 million years later, 1.5 billion years from now, the sun has brightened further. The planet has warmed further, and something happens that has not happened to Earth since its very early history. The oceans begin to evaporate. This is not a metaphor or a poetic description. It is a physical process, the same process that happened to Venus, and that the brightening sun will eventually apply to Earth. As global surface temperatures rise above roughly a critical threshold, the amount of water vapor in the atmosphere increases dramatically. Water vapor is itself a greenhouse gas. More water vapor warms the planet further. More warming means more evaporation. More evaporation means more water vapor. The feedback cycle amplifies until the oceans cannot be sustained as liquid at the surface. The process of ocean loss will not be quick in human terms. It will take tens of millions of years for the evaporation to proceed. The deeper oceans will be the last to go. The pressure of water above keeps the deep ocean liquid, even as surface temperatures rise. But progressively the oceans will thin. The shallow seas will go first. The continental shelves will become exposed. The ocean basins will shrink, and eventually the last liquid ocean, deep, hot, pressurized, will give way to an atmosphere saturated with water vapor. Water in the upper atmosphere is broken apart by ultraviolet. Light from the sun, the hydrogen, the lightest element, reaches escape velocity and is lost to space. The oxygen reacts with surface materials. Over time, the water that made up Earth's oceans does not just evaporate. It is destroyed. The hydrogen atoms escape. The planet loses its water permanently. This is exactly what happened to Venus. Venus, once possibly an ocean world, lost its water through this same process. The runaway greenhouse effect evaporated the oceans. Ultraviolet photolysis broke the water molecules, and the hydrogen escaped to space. Venus today is effectively bone dry. It retains only trace amounts of water in its lower atmosphere, a fraction of 1% of what Earth's oceans contain. Earth will follow Venus into this dry state approximately 1.5 billion years from now. The models have uncertainty ranges of hundreds of millions of years in either direction. Some analyses suggest the oceans could persist as long as 2 billion years from now, depending on the exact rate of solar brightening and the details of atmospheric chemistry. But the general timeline is robust. Without liquid oceans, without the carbon silicate cycle that depends on them, and without the temperature moderation that the oceans provide, the surface of Earth will become uninhabitable for any life that requires liquid water. The deep biosphere, the community of microorganisms that live not at the surface, but kilometers underground, in rock pores and hydrothermal systems, may persist longer than surface life. These organisms do not depend directly on sunlight or the surface ocean. They live on chemical energy from the reactions between rock and water. As long as liquid water exists somewhere in Earth's crust, which it may for some time after the surface oceans are gone, these deep organisms may survive. But even the deep biosphere has limits. As the surface heats and the deep rock heats with it, the temperature conditions in which even the most heat-tolerant organisms can survive will be exceeded, layer by layer, from the surface downward. The zone of life will be pushed progressively deeper into the crust, and eventually, even the deepest rock will be too hot. The Cambridge University paper we referenced earlier, the one studying the lifespan of the biosphere, put the mean temperature limit clearly. It calculated that Earth's mean surface temperature will reach 100 degrees Celsius, the boiling point of water at standard pressure, in approximately 1.63 billion years. At that temperature, liquid water cannot exist at the surface. The last surface liquid water will have been reached. Earth, 1.5 to 2 billion years from now, will have joined the ranks of the dead worlds. The same category of planet we explored in episode 8 of this series. Barren, dry, atmospheric chemistry reverting to prebiotic conditions. Our world will become the thing we have feared finding everywhere else in the universe. A once living planet, now silent. Earth, by 4 billion years from now, is a dead world. No oceans, no complex life, no oxygen in the atmosphere. The surface is hot, dry, probably geologically less active as the interior has cooled and plate tectonics has slowed or stopped. The planet is still here, still orbiting the sun, still Earth in the sense of being the same rocky body, but unrecognizable as the blue living world we know today. And now, something extraordinary is happening to the galaxy it is embedded in. For billions of years, the Andromeda Galaxy, the largest member of our local group, a spiral galaxy containing roughly 1 trillion stars, about twice the stellar population of the Milky Way, has been moving toward us. Not fast by cosmic standards, about 100 kilometers per second, but consistently, persistently, drawn by the gravitational attraction between two galaxy-scale masses. A new study published in Nature Astronomy in June 2025 by Till Sawala of the University of Helsinki and colleagues revised earlier estimates of this approach, running more than 100,000 computer simulations using the latest measurements from the Hubble Space Telescope and the ESA Gaia spacecraft. The team found something unexpected. A full galactic collision between the Milky Way and Andromeda is, quote, basically a coin flip, end quote. 50-50. Not the certain, inevitable merger that had been assumed in previous analyses. The gravitational dynamics are more complex than previously modeled. The presence of nearby galaxies, the triangulum, galaxy and the Large Magellanic Cloud in particular, exerts gravitational influences that either increase or decrease the probability of collision depending on their exact masses and trajectories. The uncertainty in those masses means the outcome is genuinely uncertain. In roughly half of the simulations, the Milky Way and Andromeda do not collide directly. They pass close to each other, within perhaps 500,000 light years, close enough for significant gravitational distortion of both galaxies, but not a full merger. In the other half, they do collide and eventually merge into a single large elliptical galaxy, which astronomers have nicknamed Milkomeda. Either way, the night sky of Earth, if anyone were there to see it, would be spectacular in ways that are difficult to describe. Even in the non-collision scenario, Andromeda approaching within 500,000 light-years would appear as an enormous galaxy spanning much of the sky. Not the faint smudge of the current Andromeda, barely visible to the naked eye on a dark night, but a band of light dominating one hemisphere of the sky with a brightness rivaling the Milky Way band. In the collision scenario, the experience would be different again. The galaxies would not crash in a single event, but would interpenetrate slowly, over hundreds of millions of years. Stars would rarely collide directly. Stars are far too small and far too sparsely spaced for direct stellar collisions to be common. But gravitational perturbations would scatter stars into new orbits. The neat spiral arms of both galaxies would be disrupted. Vast streams of stars would be flung into intergalactic space. Gas clouds would collide and compress, triggering bursts of new star formation. The Sun and the Solar System, what remains of the solar system by this point, would survive the collision physically. The probability of the Sun having a close encounter with another star is very low. Stars are widely enough spaced that even a galactic merger does not typically produce stellar collisions. But the Sun's orbit through the galaxy would be changed. It might be flung to larger galactic radii. It might end up in a different position within what was once the Milky Way. Earth, by 4 billion years from now, is a dead world. The Andromeda collision, if it occurs, is a spectacular backdrop to that desolation. A cosmic event of extraordinary beauty, visible from a planet on which no eyes remain to see it. The most dramatic transformation in the history of our galaxy's neighborhood, playing out over a surface of cracked rock and sterile heat. But the galaxy collision is not what ends the Earth. That is the Sun's job, and the Sun's most dramatic transformation is still coming. The Sun is a middle-aged star. It is 4.6 billion years old. Its expected main sequence lifetime, the period during which it fuses hydrogen into helium in its core, producing energy at a stable rate, is approximately 10 billion years, which means it has roughly 5 billion years remaining. Throughout those 5 billion years, the Sun will continue to brighten slowly. The changes will be too slow for any generation of humans to notice, but the accumulated effect will be enormous. By the end of the main sequence, 5 billion years from now, the Sun will be roughly 1.5 times more luminous than it is today. Then, the main sequence ends. When the hydrogen in the Sun's core is exhausted, the core will contract under gravity. The temperature of the contracting core will rise. Eventually, the temperature will be high enough to ignite hydrogen fusion in a shell surrounding the core. This shell-burning phase causes the outer layers of the Sun to expand dramatically. The Sun will swell. At first, the expansion is modest, a few tens of %, but as the core contracts further and the shell burning moves outward, the expansion accelerates. The Sun enters the red giant branch. It becomes what we call a red giant, a star with an extended, tenuous outer envelope and a hot, compressed core. How large does the Sun become? The calculations give a maximum radius of approximately 1 to 1.2 astronomical units. 1 astronomical unit is the current distance from the Earth to the Sun, which means the Sun, at its maximum red giant radius, will expand to approximately the current orbit of Earth, possibly somewhat beyond. Mercury will certainly be engulfed. Venus will certainly be engulfed. Earth sits right at the edge of the uncertainty range. A paper by Dimitri Veras at the University of Warwick summarized the situation. The Sun will definitely consume the 2 inner planets and spare Mars. But Earth sits right in the ambiguous zone between destruction and survival. The ambiguous zone, whether Earth is swallowed or not, may come down to a detail in the physics of how the Sun loses mass during the red giant phase. As the Sun expands, it loses mass. Its outer layers are only weakly bound by gravity and drift away into space as a stellar wind. This mass loss means the Sun's gravitational pull weakens, and as the gravitational pull weakens, the planet's orbits expand. They drift outward, moving away from the expanding Sun. If Earth drifts outward fast enough, if the Sun loses mass quickly enough, the planet might narrowly escape engulfment, ending up in a wider orbit around a smaller, hotter remnant. If the mass loss is insufficient, or if the drag of the Sun's outer atmosphere catches Earth before it can drift away, the planet spirals in and is destroyed. Either way, Earth in its current form does not survive the red giant phase. Even in the scenario where Earth is not engulfed, the planet will have been subjected to heating so extreme for hundreds of millions of years during the red giant's gradual expansion that any surviving rock will be sterilized, melted at the surface, and stripped of any remaining atmosphere. The Earth that emerges on the far side of the red giant phase, if it emerges at all, will be a bare molten rock, its former identity as an ocean world, and a cradle of life preserved only in the isotope ratios of its stones. The Sun's red giant phase lasts approximately 1 billion years. During this time, some extraordinary things happen in the outer solar system. The outer planets, Jupiter, Saturn, Uranus, Neptune, will not be engulfed. They are too far away, too massive, too well established in their orbits. But they will be heated. The moons of the outer solar system, some of them, currently, with subsurface liquid oceans, may experience a brief period of surface warming as the luminosity of the Sun increases dramatically. Europa's ice shell may thin, Titan's nitrogen atmosphere will warm, Enceladus's geysers will increase in intensity. Some researchers have speculated that if life had somehow established itself in the subsurface oceans of Europa or Enceladus, it might be able to move toward the surface during the red giant phase, exploiting the brief warm period before the Sun's luminosity peaks and then declines. This is speculative, but it is a reminder that the end of life on Earth does not necessarily mean the end of life in the solar system. The story of biology and planetary habitability is longer than the story of any one world. After the red giant phase, the Sun will shed its outer layers entirely. A shell of gas, the material that once made up the Sun's outer envelope, will expand outward into space, glowing briefly as the radiation from the contracting remnant ionizes it. This glowing shell is called a planetary nebula. Despite the name, it has nothing to do with planets. It is simply what a dying medium-mass star looks like from the outside as it sheds its outer layers. The planetary nebula will be visible from anywhere in the local galaxy for perhaps 10,000 years, a brief but beautiful cosmic event. Then it will disperse, the gas fading into the interstellar medium, and what remains will be the Sun's core. The Sun's core, compressed into a sphere roughly the size of Earth but containing perhaps half the Sun's remaining mass, will be a white dwarf, a dense, hot object made primarily of carbon and oxygen, the ashes of the nuclear fusion that powered the Sun for 10 billion years. No more fusion occurs. The white dwarf is supported against gravitational collapse by a quantum mechanical effect called electron degeneracy pressure. It generates no new energy. It simply radiates its stored thermal energy into space, cooling over trillions of years. The outer planets will have survived. Jupiter, Saturn, Uranus, and Neptune, now in wider orbits around a much fainter Sun, will continue to orbit the white dwarf. Their orbits will be stable for essentially unlimited time, but without a luminous star to heat them, the outer solar system will be cold, dark, silent. Earth, in this scenario, will either have been engulfed during the red giant phase, or will survive as a scorched, airless rock in an orbit closer to the white dwarf than Earth currently is relative to the Sun. Either way, it is no longer a habitable world. No water, no atmosphere, no chemistry that has any relationship to life. A geological specimen orbiting in silence. White dwarfs cool very slowly. The Sun as white dwarf will remain warm enough to faintly glow for hundreds of billions of years. Eventually, over timescales far beyond the current age of the universe, it will cool to the point of invisibility. A black dwarf, the theoretical final stage of a white dwarf's evolution. No black dwarfs yet exist in the universe. The universe is not old enough for any white dwarf to have cooled that far. But in the far future, the Sun will join the ranks of those dark, cold, invisible objects drifting in the darkness of a very different galaxy. And somewhere in the vicinity, perhaps still in orbit, perhaps scattered into interstellar space by gravitational interactions during the red giant expansion, the remains of the planets will drift. Not living, not dead in the way we usually mean, because they never had life to begin with by this point. Simply matter, rock, metal, the material of which the solar system was made, redistributed into new configurations by 5 billion years of stellar evolution. We have followed the Earth to its end. We have watched, in imagination, the slow process by which a living world becomes first a hot desert, then an airless rock, then a piece of molten debris in the expanding envelope of a red giant, and finally, perhaps, a surviving stone in the cold vicinity of a white dwarf. But the story of life does not necessarily end there, because Earth is not the only world and the Sun is not the only star. The red dwarf stars, the most common type of star in the galaxy, making up 70% of all stellar mass, will continue to burn for 10 trillion years or more after the Sun has become a white dwarf. In 10 trillion years, the Sun will be a cooling, invisible black dwarf, and the red dwarfs will still be fusing hydrogen in their cores. The universe, 10 trillion years from now, will not be dark. It will be populated by a vast population of slowly glowing red stars. If life exists on planets around those red dwarfs, and we explored the difficulties of that proposition in episode 8 of this series, it could potentially persist for a time beyond anything we can comfortably contemplate. Not billions of years, not tens of billions, trillions. There is also the question of whether Earth-based life needs to end with Earth. The time available between now and the end of Earth's habitable surface, approximately 1 billion years at a minimum, is, in principle, enough time for life to spread beyond Earth if it develops the technological means to do so. 1 billion years is roughly the time it took complex multicellular life to evolve from the first simple eukaryotic cells. It is a very long time, long enough, potentially, for the descendants of Earth's biosphere to establish themselves elsewhere. This is not a prediction. It is a possibility. The history of intelligence on Earth, about 300,000 years for anatomically modern humans, and perhaps 10,000 years for civilization, is so brief compared to the remaining habitable period that it is impossible to say what could be accomplished in the remainder. In 1 billion years, human civilization has had essentially no time at all to develop. We cannot project what 1 billion more years of development might look like, but we can note that the physical resources available for life to continue in the solar system, in the galaxy, are enormous. The outer solar system will be briefly warmed by the red giant sun. The moons of Jupiter and Saturn may become habitable, even if briefly. And beyond the solar system, the galaxy contains billions of star systems, most of them younger than our own, many of them with rocky planets that have not yet exhausted their habitable periods. The end of life on Earth is not the end of life in the universe. It is the end of a chapter. The same chapter end that has happened, presumably, billions of times across billions of worlds as their stars evolved and their climates shifted beyond the tolerance of whatever forms of life had developed there. Earth's chapter is about 1.5 billion years from its end. The book is longer. The deep biosphere, the microorganisms living kilometers underground in rock, may outlast surface life by hundreds of millions of years. They are insulated from surface temperature changes by the rock above them. They do not depend on sunlight. As long as the geological processes that power them, radioactive decay, hydrothermal venting, chemical reactions with rock, continue to operate, they have an energy supply. Some models suggest the deep biosphere could survive for 1 billion or more years after the surface becomes uninhabitable, and after the deep biosphere finally succumbs to the rising rock temperature, what remains is not nothing. It is the chemistry of a world that was once alive. Isotope ratios in rocks that record the metabolic processes of ancient organisms. Organic molecules embedded in ancient sediments. The carbon-12 to carbon-13 ratios that are the fingerprint of biological carbon fixation. Long after the last organism dies, the rocks of Earth will carry the chemical record of 4 billion years of life. If, billions of years from now, some other intelligence were to visit the dead Earth, assuming it survives as a remnant world around the white dwarf, they would find in its rocks the evidence that this was once a living world. The same evidence that we find in ancient Mars rocks, in the carbon ratios of meteorites, in the isotopic signatures of the solar system's materials. The record of life on Earth will outlast the life itself. We have traveled from now to the end of all things. 250 million years to Pangea Ultima, 500 million years to the death of the last plant, 1 billion years to the oxygen collapse, 1.5 billion years to the evaporation of the oceans, 4 billion years to the Andromeda approach, 5 billion years to the red giant sun, and beyond, to the white dwarf, to the cold, to the silence. It is a long journey, and in some moods, it can feel like a dark one. The accumulation of endings, each more final than the last, can produce a kind of vertigo. The sense that everything we love, every forest, every ocean, every face, every piece of music, every conversation, is temporary, fragile, doomed. But there is another way to hear this story. We are living in the middle of Earth's habitable period. Not at the beginning, which is already 4 billion years in the past. Not at the end, which is still roughly 1 billion years away. We are here now, in the long, warm, stable middle. In the chapter of Earth's history that has oceans and oxygen and forests, and creatures with the extraordinary capacity to understand their own situation. The conditions that make this possible. The atmospheric chemistry. The carbon cycle, the magnetic field, the plate tectonics, the liquid ocean are not permanent. We knew this in a vague way before this documentary, but now we know it precisely. We have numbers, we have timelines, we have the outputs of 400,000 computer simulations telling us, with careful scientific uncertainty, when each phase of Earth's habitable period will end. And what those numbers reveal is not despair. What they reveal is the extraordinary specificity of now. The fact that we are alive on this particular planet at this particular moment in its history, not in the methane-rich early atmosphere, not in the snowball Earth, not in the post-oxygen collapse, is not guaranteed. It is the product of a long, complex, improbable history of conditions being met, challenges being survived, and time being given. We are, right now, inhabiting the gift of a world with liquid oceans and breathable air, the gift of a sun that is bright enough to warm us and distant enough not to cook us, the gift of a carbon cycle that has been keeping the atmosphere in balance for 4 billion years, the gift of enough time, 1 billion years of it still remaining, for life to continue to evolve, to understand, and perhaps to find its way beyond the world that made it. The end of all life on Earth is a fact. The timeline is known. The mechanisms are understood. And knowing all of this does not diminish the world we have. It deepens it. Every ocean is more beautiful knowing it will eventually evaporate. Every forest is more precious, knowing the carbon cycle that feeds it will eventually fail. Every breath of oxygen is more extraordinary, knowing that 1 billion years from now, there will be no oxygen to breathe. You are here. This moment is here. The planet is alive. That will not always be true. For now, it is. Sleep well.